Thanks so much. Thanks, Nina, Trina, and Chris, and other organizers for organizing this wonderful workshop. It's so sad that neither Alex and nor I could be there in person, but we very much hope that in the future, there will be time for us to actually meet in person. So today, Alex and I are going to present on our joint work, Bayesianism Redux. Before we start, we should say that this is not very much a project in Bayesian cognitive science, though it does bear has a intimate connection to many of the things that have already been discussed in previous talks, in particular the optimality of Bayesianism. So we're going to ask, as you'll see, and indeed this is the first slide, the primary question that we're interested in discussing today is whether Bayesianism is indeed optimal. So it's not the question whether or not we should trust the optimal modeling, but rather whether or not Bayesianism lives up to the hope of being the optimal in the first place. Okay, so first let's take a step back and just ask, well, seems like a very common assumption, especially amongst epistemologists, philosophers, and economists, cognitive sciences. Well, rational agents should be Bayesians. But you might wonder, well, why should that be the case? In particular, why should rational agents update by Bayesian conditionalization? Well, in philosophy, there's a well-known class argument that answers that question, known as instrumentalist arguments, or we might call optimality arguments. The rough idea is rational agents should update by Bayesian conditionalization because it is optimal, in particular because it helps you avoid being dashboarded, it maximizes accuracy, it maximizes the expected pragmatic utility of your future decisions, so on and so forth. And those are merits. So if you want to do that, then you should update by Bayesian conditionalization. Okay, so far so good, except that there's a wrinkle with these arguments. Namely, they all assume that the agent's evidence is partitional in the sense that we're going to make precise later. And it turns out that if you drop that assumption, then all the arguments break down in non-partitional cases. It turns out that Bayesian conditionalization is no longer optimal in those circumstances. So at this stage, two questions arise, and we aim to address each of them in turn in this talk. The first question is, well, why should all these arguments break down in non-partitional cases? Is there any unified explanation for the failure of optimality arguments in non-partitional cases? And we think there is, so that's one thing we're going to do in this talk. And another thing you might wonder is, well, given that all these arguments fail in non-partitional cases, is there anything else we can say in favor of Bayesian conditionalization in those circumstances? And that would be the second part of the talk. So we propose a positive justification of Bayesian conditionalization, which is still very much an optimality argument in favor of Bayesian conditionalization without the assumption that the agent's evidence is partitional. So this is an overview of the structure of the talk. So first, we're going to introduce some technical preliminaries, in particular, define what we mean by non-partitional evidence. And then we're going to try to achieve each of the goals. In turn, we're going to first provide a unified explanation for the failures of traditional instrumentalist arguments for Bayesian conditionalization in non-partitional setting, and then gives our positive proposal of an optimality argument for Bayesian conditionalization in non-partitional cases. Okay, so some technical preliminaries. So for the rest of this talk, we're going to work in a finite state space represented by W, and use delta W to denote the set of probability distributions over this finite state space. And propositions in this framework are going to be represented by subsets of the state space. So all these are standard terminologies in the literature. The first piece of technical jargon we're going to introduce is that of learning situation. And heuristically, you can think of a learning situation as a specification of all possible courses of learning experiences an agent might undergo during a course of time, for example, this afternoon. And formally speaking, we're going to represent that learning situation as a function from words to propositions. And intuitively, EW, or each word W, can be interpreted as representing the strongest proposition that the agent is going to learn in her learning situation at word W. So this might sound abstract. We're going to work through a concrete example shortly. Lastly, an updating plan or an updating strategy relative to a prior and a learning situation is represented by a function that maps a word to a probability distribution, representing the posterior probability that the agent plans to adopt given her prior and the learning situation at W. So in particular, we say a plan is E constant with respect to a learning situation, just in case it doesn't give different recommendations when the agent learns the same thing. So lastly, in this framework, Bayesian conditionalization relative to a prior and the learning situation corresponds to an updating plan, which says basically as what you might expect, at each word update by adopting the probability, which is your prior conditionalizing on the strongest proposition that you have learned at that word. So that is Bayesian conditionalization in this framework. Okay, as I said, we're going to work through a concrete example. So suppose someone tosses a four-sided fair die. In this case, let's just assume there are only four possibilities. The die lands on side 1, 2, 3, 4, respectively. And so we have four states. And in this case, suppose the agent will learn whether the die landed even or odd. So if the die landed on 1, then the agent is going to learn that the die landed on an odd number. If the die landed on 2, the agent is going to learn that it landed on an even number, so on and so forth. In this case, we can represent the agent's learning situation by a function that maps all the odd word to the set W1, W3, and even word to the set W2, W4. And Bayesian conditionalization just says what you expect it to say. Well, if you are at a word where the die landed on side 1, then Bayesian conditionalization says, given that you will learn that the die landed on an odd number, then you should assign credence 0 to the even words and 1/2 to the odd words. Similarly, in the even case. So far, so good. Well, in the previous case, you might think, well, Bayesian conditionalization gives you sort of the intuitive version of what you should do in that learning situation. Indeed, how else should the rational agent update in that situation? Well, as philosophers in particular, we want to ask for a bit more than just intuition. We want to ask for a principled justification for why should rational agents update by Bayesian conditionalization. And as alluded to above, there is something that we can say in favor of Bayesian conditionalization, namely it is optimal. In particular, you can divide the optimality arguments into two groups. The first group says, well, Bayesian conditionalization is optimal in the sense that it avoids bad consequences. In particular, it helps you avoid being Dutch booked and also helps you avoid being accuracy dominated. Neither sounds very pleasant. So that's why you should Bayesian conditionalize. And here's more. It also helps you achieve the best outcome. In particular, it maximizes expected accuracy and also maximizes expected value of your future decisions. If you value either, then you should update by Bayesian conditionalization. So far, so good. However, as also noted before, there is a wrinkle with this class of optimality arguments, namely they all rely on the following assumption that learning is transparent in the sense that in any learning situation, the agent learns that she has or has not learned a proposition. So if an agent learns a proposition, she also learns that she has learned that proposition. If the agent doesn't learn some proposition, then she also learns that she has not learned that proposition. That's what we mean by learning is transparent. In the formal framework, you can represent that assumption via this biconditional. And for those people who are familiar with epistemic logic, this is equivalent to the assumption that the epistemic accessibility relation in the model is an equivalence relation, or alternatively put, the agent's possible evidence forms a partition of the state space. As you can see in the previous example, that's precisely the case. So that is a case where the agent's learning is transparent by stipulation. Okay, so we have this host of optimality arguments for Bayesian conditionalization, but they all rest on this, or at least they all implicitly assume that the agent's learning is transparent. A natural question to ask at this point is, well, is that assumption plausible? It turns out that this is sort of a controversial question in the literature. So first, some people think, at least for boundedly rational agents, learning can fail to be transparent. Here's an example extracted from Sherlock Holmes. So Dr. Watson and Sherlock Holmes are having this conversation. Dr. Watson asked Sherlock, "Is there any other point to which you would wish to draw my attention?" Sherlock replied, "Well, to the incident of the dog in the nighttime." Dr. Watson is puzzled. "Well, the dog did nothing in the nighttime." Sherlock remarked, "Well, that was a curious incident." So on the prima facie reading of the case, it seems like Dr. Watson might be described as being in a non-transparent learning situation. Namely, he learns that the dog didn't bark at night, and yet he failed to take notice of the fact that he learned that the dog didn't bark at night. So he learned something, but he didn't learn that he has learned it. And you might think that is just a sign of rational failure on the part of Dr. Watson, and one may very well agree. Yet, on the other hand, you might think that is the kind of rational failure that we should make room for in a more reasonable modeling of agent. For example, as economist Dinotopoulos remarked, Sherlock Holmes is a perfectly rational Bayesian optimizer that economic models assume all agents are like. Yet most economic actors are probably much more like Dr. Watson than like Sherlock Holmes. They usually take signals at face value, and they often take no notice when something doesn't happen. So if we want a more reasonable, realistic model of agent, then probably we want to make room for non-transparent learning situations as well. So that's the first motivation. Boundedly rational agents may fail to learn what they have or have not learned. And even more, some philosophers have thought that even ideally rational agents may find themselves in non-transparent learning situations as well. And here's an example we adapted from Williamson 2000. So suppose Dana is making cookies. Unfortunately, her scale is broken, so she has to estimate the amount of butter that she'll use by hand. She takes out the leftover butter, which she knows to weigh no less than 15 grams and no more than 20 grams. Dana is quite experienced. In particular, she knows that her estimate of the butter after weighing the butter in her hand would be off by no more than 1 gram of margin. And yet she also can't get more precise either because she's not a scale herself. So here's a simple model of Dana's learning situation. Basically, at each word, for example, suppose that the butter actually weighs 18 grams, then by stipulation, after weighing the butter in her hand, Dana would learn that the butter weighs between 17 and 19 grams, but nothing more precise. On the other hand, if the butter weighs 17 grams, then Dana would learn that it weighs between 16 and 18 grams, but nothing more precise. In particular, as you can see from the diagram, in this case, Dana is in a non-transparent learning situation because her possible evidence overlaps with each other. It doesn't form a partition, so given our equivalent characterization of the assumption, this is a case of non-transparent learning situation. In particular, the assumption here is that when Dana learns that, for example, the butter weighs between 17 and 19 grams, she isn't certain that the butter actually, she learns that the butter weighs between 17 to 19 grams. So she learned something, but she isn't certain that she has learned that thing. Okay. As noted before, whether or not there are genuine cases of rational non-transparent learning situations is a very controversial topic in the literature. And for the rest of this presentation, we're actually not going to weigh in on that debate. Instead, we're just going to take for granted that rational, bounded, or ideal agents can sometimes find themselves in non-partitional learning situations. That is, they can fail to learn what they have or have not learned. The question we're interested in asking is, well, in those cases, assume that they find themselves in those situations, how should they update on their evidence in such circumstances? And your first test might be, well, just Bayesian conditionalize. It worked well in transparent cases. It should work well in non-transparent cases. As it turns out, if your reason for rational agents, for thinking that rational agents should update by Bayesian conditionalization is the optimality argument, for example, it avoids dashboards or it maximizes expected accuracy, then turns out that those reasonings actually don't go through in the non-transparent cases. Instead, they support a different updating rule known as meta-conditionalization. And roughly, the rule says at each word, if E is the strongest proposition that you have learned, then update by conditionalizing on the proposition that you have learned E. In particular, if you're in a non-transparent learning situation, namely, the strongest proposition comes apart from the proposition that you have learned that proposition, then meta-conditionalization disagree with Bayesian conditionalization. And indeed, they coincide if and only if the learning situation is transparent. The agent always learns what they have or have not learned. So here's a theorem that we generalized from existing results in the literature by Zhang and Schoenfeld. So as it turns out that in general, without any assumptions about learning situations, the updating rule that maximizes or is optimal in those situations, it's actually not Bayesian conditionalization, but meta-conditionalization that we just introduced. In particular, meta-conditionalization is not accuracy dominated, it's not attributable, and it maximizes the expected accuracy as well as expected pragmatic utility. The optimality of Bayesian conditionalization follows from this theorem as a corollary, assuming that the agent is in a transparent learning situation, because in those cases, as remarked before, meta-conditionalization coincides with Bayesian conditionalization. But whenever they come apart, Bayesian conditionalization becomes suboptimal in each of the four senses. So this is the situation that we inherited from the literature. As we said before, there are two questions that you can ask at this point. First, why do this happen? Is there anything more general we can say about why Bayesian conditionalization becomes suboptimal in those circumstances? And more importantly, as Bayesians, can we say something in favor of Bayesian conditionalization, despite the failures of these traditional fundamentalist arguments? And now I'm going to pass on to Alex to say a bit more on each point.
Great. Thank you, Snow. And as Snow said, many thanks to the organizers. And I hope that there's a chance to meet in person at some point in the not too distant future. Just going to share my screen here. Okay, so jumping to what Snow described as the first goal of the talk, which is, can we give a sort of unifying conceptual explanation for why this is happening, why Bayesian conditionalization is suboptimal in all these different sort of instrumentalist senses in non-partitional situations. And the answer that we want to give, or the explanation that we want to give, is related to a principle of rationality known as the principle of reflection. So just a brief introduction to that. So suppose this is a variant of the Dana butter case. So suppose that Dana knows before she weighs the butter that upon weighing the butter, she's going to become rationally certain that the butter weighs 18 grams. Well, intuitively, if somehow she already knows that in advance upon weighing the butter, she's going to become certain that the butter weighs 18 grams, then she should just be confident now that the butter weighs 18 grams, at least if she knows that she's not going to forget anything in the course of the learning experience and so on. So more generally, and this is a very rough gloss of the idea behind the principle of reflection, the thought is that rationality requires that you defer to the credences that you plan to adopt. All right, so it's an informal gloss. Now, it's a bit of a mouthful what's on the screen right now, but this is the precise notion of sort of satisfying reflection that will be important in this case. So fixing some prior, we're going to say a plan is self-reflective if it satisfies the equation on the screen here. Roughly, you can read what this equation is saying is that the updating plan is worthy of deference. In particular, if you were to take the prior and conditionalize it on what the plan recommends. So take the prior and tell the prior, the plan recommends this posterior. Then conditional on that, the prior would then adopt the plan. In other words, the plan is worthy of deference for all the different possible recommendations of the plan. So if that holds, then we say that the plan is self-reflective with respect to the prior. Okay. Now, given some plan which may or may not be self-reflective, we can define the reflective version of that plan, which is basically just the result of taking the prior and conditionalizing it on information about what that plan recommends. So we'll denote the result of doing that by this F tilde. So a different way of stating when a plan is self-reflective is simply that a plan F is self-reflective when it equals its reflective version, when F equals F tilde. All right, so with that out of the way, here's the first crucial observation. So in partitional learning situations, you can show that Bayesian conditionalization is always self-reflective. But the crucial thing is that in non-partitional situations, Bayesian conditionalization is not self-reflective. It's not worthy of deference. And in particular, its reflective version is precisely the plan of meta-conditionalization that Snow was describing earlier. Okay, so that's the first crucial observation. Now here's the other observation. So if you take a plan what this says is that if a plan is not self-reflective, then its reflective version is going to do better than it in terms of accuracy. And moreover, the original plan is going to be Dutch bookable, so on and so forth. Okay, so this result describes what happens if we have a plan and its reflective version. And it says the reflective version, to the extent that it differs from the plan, is always going to do better instrumentally. It's always going to be more optimal. But what if we have two plans, which one's not the reflective version of the other, they're just two self-reflective plans hanging out? Which is better in that case? Well, it turns out that once we sort of sorted out the issue of reflection, then what matters is how sensitive the plans are. So one more piece of sort of technical jargon or machinery here. So we say that one plan F is at least as sensitive as another plan F prime if whenever that first plan gives the same recommendations, that second plan also gives the same recommendations. So basically this is saying that the more sensitive a plan is, kind of the more fine-grained it varies with respect to its input from the world. Now, as you might expect, if you have two plans that are both self-reflective, but one is strictly more sensitive than the other, then that plan that's more sensitive kind of seems to have at least a face value advantage. Now, what this result says is actually in that situation, that more sensitive plan is always going to do better instrumentally than that less sensitive plan. Again, in all the different senses, according to all the different instrumentalist metrics. Okay, so putting these two observations about reflection on the one hand and sensitivity on the other hand together, which plan overall is best? Well, in general, that's sort of a cheating question because the answer kind of depends on initially what set of plans are we thinking of as available that the agent can implement or follow. So suppose we do fix some, bag of plans where we say these are the possible plans that the agent could actually implement or follow. Now, what these two results together entail is that if there is a self-reflective plan in that bag of plans that's more sensitive than all the other self-reflective plans, then that is always going to be the instrumentally best plan in all the different senses. So an example of this, if we just let the bag of available plans just be any old plan that could be stated, mathematically as a function from worlds to posteriors, then the self-reflective plan in that bag of all the plans that's most sensitive is just going to be the omniscient updating plan, which says that the agent will become certain in the maximally certain in all the truths and have zero credence in all the falsities. Now, of course, that's not a very realistic choice of the set of available plans, because you might think the omniscient updating plan is not something that's generally available to agents. So a slightly more realistic case would be if we let the set of available plans be precisely the set of all and only the E constant plans that Snow is describing, those that give the same recommendation given the same evidence. If that's how we're sort of circumscribing the set of available plans, then we get the most sensitive self-reflective plan in that bag of plans is precisely meta-conditionalization. Okay, so that's an example, but note that the result is kind of abstract to any set of possible choice of set of available plans. Indeed, and actually this is, I think, the most crucial observation here, note that evidence or the learning situation isn't really playing any essential role in these instrumentalist considerations. So I think the most important punchline from this part is that actually instrumentalist considerations don't care about how sort of well a plan is responding to the evidence, in the sense of, for example, being rigid with respect to the evidence, which is kind of what the characteristic property of Bayesian conditionalization is. Rather, instrumentalist considerations care about two things. First of all, whether the plan kind of respects itself, whether it's worthy of deference according to the prior. And second, how sensitive the plan is. Neither of those two things are directly related to a kind of responsiveness to evidence or rigidity in the face of evidence. And so that's intuitively why we're getting this kind of result that, even though Bayesian conditionalization seems so intuitive, at least especially on kind of evidentialist type reasoning, it's not coming out as instrumentally optimal in any of the senses. Once we sort of weaken this assumption that then splits the connection between a kind of rigidity to the evidence and being reflective. Okay. All right, so now let's sort of take a pause here. So for the Bayesian, as Snow was foreshadowing, this is kind of an undesirable result, at least to the extent that we want instrumentalist arguments in favor of Bayesian conditionalization. So a natural question to ask here is, maybe we could take a step back and think about whether there's a different way of approaching this question, both of how to formulate and evaluate plans that might give us a different outcome. And that will transition to the last part of the talk, which I'm going to try to go through as quickly as possible. And that's our positive proposal for a different way of approaching this that yields a more positive verdict for Bayesian conditionalization. Okay, so at the beginning of the talk, we kind of followed what the standard setup was in the literature, which is fixing a learning situation, and then defining and updating plan in the way that we did, which was a function from worlds to probability distributions. But what if we took a different approach, a kind of different modeling framework, if you like, where we don't fix any particular learning situation in advance? And instead, we define a plan as not a function of worlds, but a function of propositions. So I think this is what's here in blue is actually probably the more natural thing if you just took someone from this conference and pulled them aside and say, can you give me a very precise formulation of what Bayesian conditionalization says? It's probably going to look something more like this. Bayesian conditionalization, given a fixed prior, takes different pieces of possible evidence as input and then outputs a posterior given that evidence as input. So what's written here is how you would write Bayesian conditionalization in this new format as a function of the possible evidence to the posterior. And a note, this is something that we can come back to in Q&A because it's kind of important to why our positive proposal ultimately works. Because we're not fixing any learning situation in the background, it's actually not even possible to state meta-conditionalization as kind of a legitimate updating plan in this framework. Okay. So if we're on board with this slightly amended framework, we can now ask, okay, in this setting, which updating plan is instrumentally best? Now we immediately hit a snag because the previous notions of expected accuracy, Dutch bookability, and so forth don't immediately carry over to this new setting, which might be why, even though it has some sort of natural, nice features, this kind of setting is not usually used. So just to give a sense of what kind of problems you run into, consider expected accuracy. So this equation here is how we would normally define the expected accuracy of an updating plan. So we would take the accuracy of the plan's recommendation at a world, and then we would take the weighted sum over that across all the different worlds as weighted by the prior. But notice that's assuming that the updating plan is expressible as a function of worlds. And because we don't have any learning situation fixed in the background, there's no easy way of translating this equation that you see here to something which has the updating plan sort of taking evidence as a function rather than worlds as a function. Okay. And this is sort of Snow and I's sort of like idea for what to do here. The thought is that while we can't define a notion of expected accuracy in the usual sense, we can define a notion of what we call expected total accuracy. So what's expected total accuracy? So what we do is, given a world, we want to know sort of how well does the updating plan perform accuracy-wise at that world. So by the way, we're focusing on accuracy now, for example, but you can give a sort of similar proposal for Dutch books and so on. So given a world, how well does an updating plan perform at that world? Well, what we can do is we can say, well, let's look at all the different recommendations that updating plan gives for all the different pieces of possible evidence that are in principle learnable at that world. So that's basically that's why we call it total, because we're sort of taking the sum of the accuracy for all the different pieces of possible evidence that are learnable at the given world, that are compatible with that world. And then just as before with expected accuracy, we can then weight that score by taking the weighted sum, weighing worlds according to the prior. A small side note here, there's other ways you might be initially inclined to define total accuracy by, for example, taking a sum over different possible learning situations rather than different possible propositions. It turns out that they give the same result, but we're happy to talk about those alternate ways in the Q&A if anyone's interested. Okay, so perhaps remarkably, it turns out that the plan that uniquely maximizes expected total accuracy in this new framework is precisely Bayesian conditionalization. So I'm going to say in a little bit how to understand this result, but just first a couple of quick notes. So first, note that nowhere in the result or this new framework do we assume that evidence is transparent or partitional. So that's the sense in which this result is general to also non-partitional situations. And as I mentioned, the result can also be extended to the other kinds of instrumentalist metrics as well. Okay, so how do we understand this result? Well, the basic idea, and this is sort of an intuitive level, the basic idea is that even though Bayesian conditionalization may not be sort of locally optimal in a given fixed learning situation, especially when that learning situation is non-partitional, that's sort of what the first half of the talk was pointing out. It's still globally optimal in the sense that if you were to just ask, kind of give me what's generically the best updating rule, I'm not going to tell you a specific learning situation. I'm just going to ask you sort of like, generically, what is the best updating rule that an agent can follow? Then it turns out that Bayesian conditionalization does the best sort of holistically when its performance is aggregated across different pieces of possible evidence or across different possible learning situations. So even though the results from the first half of the talk are sort of negative against Bayesian conditionalization, we think that ultimately this other framework and sort of way of evaluating the instrumental merits of Bayesian conditionalization is a more appropriate way. And it does give this positive verdict that Bayesian conditionalization is the best. It's almost like saying, maybe some in the audience would sort of dispute this characterization, but it's sort of saying that Bayesian conditionalization is kind of like the best heuristic, or if you just want to ask sort of what's generically the best updating rule that does the best in this global sense, it's going to be Bayesian conditionalization, even though if you were to give us a specific learning situation, give us that extra input and zoom in on that particular situation, it may not be locally optimal in that particular situation. So given this positive result, even in light of the negative results earlier, we do want to say that Bayesian conditionalization is, even in the instrumentalist sense, the best rule. And for that reason, we think that Bayes is back. All right, so that's all we have. We'll stop there for questions. Thank you so much again.